So we're looking at page 38 in the Unit 2 packet, focusing on binomial probability distributions. In terms of the power of this type of concept, it's very, very important and fundamental to the stuff that we're going to be learning down the line. In terms of level of difficulty, I can say that it's gonna start off seeming like it's very challenging, but I'll show you the ways in which we kind of pare it down to make it something that's actually rather simple. All right. Right off the bat, you see a nasty looking formula. You know, this bad boy right here that's got some stuff in it that we haven't even really talked about yet. We will talk about that C notation, but for now, we're just going to get into just how the process works rather than the why. All right. So the conditions that have to be in place in order for you to be able to work with a binomial probability distribution would be that there needs to be a fixed number of trials. Right? So if you're withdrawing 5 cards from a deck, it's not going to change from the 5 cards that you're withdrawing from the deck. It's not like after the first card you select that you can make a decision of how many more you want after that. It's always going to be 5 cards that you're withdrawing from the deck. All right? Fixed probability. So if we are talking about a deck of cards, the probability of success cannot vary from trial to trial. All right? So going back to that idea of withdrawing 5 cards from a deck, I would have to then, when I select a card from the deck, observe what that card is, maybe write it down, put the card back in the deck, shuffle it up, and then select my second card, take note of what it is, put it back in the deck, shuffle it up, withdraw a 3rd card, and 4th card, and a 5th card. All right, so that the probability of success on any one attempt never varies. All right, independent events goes hand in hand with that. If there is no change in probability from event to event, then we could assume that the events are independent of one another, and that there are 2 outcomes, either success or failure, which actually seems like it would be somewhat limiting. And it's like, well, how do we categorize things in just 2 ways? Well, if you're looking at a deck of cards, you say, well, there's 52 possible decks that you, 52 decks, geez, 52 possible cards that you can get from the deck. All right, that's true, but you could also look at it and say, well, I want to get an ace. So I can break that deck up into the cards that are aces and the cards that are not. So 2 outcomes. Right? It's aces and everything but aces. Right? So that's our 2 outcomes, either success or failure. If you're not first, you're last. It's not that dramatic, but still. So these conditions need to be in play every single time you evaluate a probability question to determine if it's binomial. Right? And if we meet those conditions, then you could use this formula. But I can tell you there's a shortcut to this formula that's involved in Desmos. Right? But I'm going to show you sort of a lengthier way of doing it first. Right? Teacher's prerogative. So here's a pop quiz. You have 5 choices, A, B, C, D, and E. And there are 5 questions. So it's a 5-question multiple choice assessment. And there are 5 choices apiece. All right. So what I'm going to do is I'm going to guess, because the teacher didn't prepare me for this. I'm not ready. I didn't even know there was going to be a quiz. Well, I guess that's the pop behind the pop quiz. How am I going to get them right? There aren't even any questions there. All right. So let me just take a guess. All right. That's my first choice. My second one, my third one, 4th one, and my 5th one. Now, is it completely random? Probably not, because I varied my choices. You know, I went from A to D to C to E and then to B. You know, was there a reason why I did that? I felt like I didn't want to leave a choice out of the mix. I really had no idea. Now, if I tell you that the answers are C, B, C, D, E. All right, so this unfair pop quiz that I just took, the teacher came along and graded it based off of the answer key. I'm still confused. I'm like, how is this even an assessment? But whatever. Turned out I got the first one wrong, and the second. Third one I got right. Wrong, wrong. All right. So I got one question right. So one question correct. All right. I mean, so I bombed that. But, I was set up for failure. Now it's saying let x equal the number of correct guesses. All right, so x could be the number of possible correct answers. We want to know, is this a binomial setting, and why? Well, if you go down to the table below, see we have a list of x, a horizontal list. Those are the number of possible correct answers. So that's what the let x equal number of correct guesses is referring to. I might have guessed none of them right, only one of them right, as it turned out here. Two of them right, 2 out of the 5, 3 out of the 5, 4 out of the 5. Maybe I got them all 5 of them right. It's entirely possible. But that's not what the question's asking. The question's asking us, is it a binomial situation? Is it a binomial setting? Well, I can say yes, because it's on the handout that says binomial probability distribution, so it must be. No. Fixed number of trials. There were 5 questions. Each had a probability of success, assuming getting the right answer is success, of 1 in 5. 1 right and the other values, the other 4 would be wrong. Independent events. We can look at that strictly from a probability standpoint, but we could also look at it from, I'll call it a common sense standpoint. If I got question 1 right, that doesn't mean I can no longer get any of the other questions right. But I could also look at it another way. This is more in line with independent events. All the choices are available to me for each question. All right? Independent events is really talking about that. You're flipping a coin, heads or tails, those are your outcomes. No matter how many times you flip the coin, you're always going to have heads or tails as your possible outcomes. So independent events, all choices are available. I'll say always available. All right, all choices are always available. All right, so I selected choice A for the first question. It would be dependent events if I were to say, well, I've already used A, can't use it again. All right, for the second question I used D, so then I would no longer be able to use D after that. Then after that, I chose C, which means I would no longer be able to use C after that. After I chose the C, I chose the D, which would actually force me to choose E for the last question. That's not what happened here, although it may seem like that's the case. I used a little bit of a scheme when I was making my choices, but not because I had to, but because I wanted to. It's a pretty close to a movie quote. If anybody knows what movie I'm quoting, send me a message and I'll give you a bonus point. Not because I have to, but because I want to. All right. So that's what I call an Easter egg. And I'll be dropping a whole lot more of those in the remainder of my videos. All right. So 2 outcomes, success or failure. I mean, that's easy enough. 2 outcomes. I could actually just rewrite what I had above in the highlight. 2 outcomes, right or wrong, I'll say. All right. So because all 4 of these conditions, 1, 2, 3, and 4, are all satisfied, we know that we're dealing with a binomial distribution. All right. Now it says calculate the probability of getting exactly 2 questions correct. Show your work. Right? This is where things get interesting, because there's a couple of ways we can handle this. One is to use this shortcut formula, but if I tell you that there's a shortcut to the shortcut using Desmos, then it kind of even takes away the need to get involved with that formula. All right, what I'll do is I'll show you the more drawn out way of doing it. All right, because we have to use the addition rule here by saying not only that you're getting 2 questions correct, we have to get specific about which 2 questions we got correct. Was it the first and the second? Was it the first and the third? Was it the first and the fourth? Was it the first and the fifth? I could say, was it the second and the first, but that's the same as saying the first and the second, right? Second and third, second and fourth, second and fifth, second, oh, I was going to say second and sixth, that wouldn't play out. Third and the first would be the same as the first and the third. Third and the second would be the same as the second and third. Third and third wouldn't make sense. It's only just getting 1 question right. All right. Third and fourth. Third and fifth. Maybe it was the fourth and the fifth. So these are the different possible ways that you can get 2 questions right out of the 5 that are available. All right, so now what we can do is we can start the process of figuring out the probability of each one. So I would say the probability of getting 1 and 2 right. All right, now that would mean that we got the first 2 questions right. All right, so we got 1 and 2 correct. And if we just kind of make a little table here, 1, 2, 3, 4, 5. I'd be saying I got the first 2 correct, but then after that I got them all incorrect, or all the remaining ones incorrect. All right. The probability of getting any one question correct would be a 1 in 5 chance. The probability of getting a question incorrect would be 4 in 5. All right, so we can run those numbers, but it's going to get pretty large pretty quickly. You know, let me open up a Desmos calculator here. And you can write this using powers, you know, just to make it a little bit more concise. But I'll get to that in a second. 1/5 times 1/5 times 4/5 times 4/5 times 4/5. So that's, you know, a funky decimal. Let's fractionalize that. I just made up a term, I think. 64, or at least I said something that probably means something different. So 3125 is the probability. So 64 over 3,125 is the probability of getting those 2 particular questions right on this assessment. All right, that's only one possible scenario. All right, now you may remember when we worked with the card questions, you know, some of the questions were things like, what's the probability that they're all, you know, the 2 cards selected were both part of the same suit, things like that. This is the same idea, because this is all or, you know, it's just a big question that's going to come back to us. That is the probability of getting the first and the third question going to be any different than the probability of getting the first and the second question correct? And really, if you think about it, if it's just the first and third that are correct and everything else is incorrect, that would be this arrangement. Right? In the end, you're still going to have 2 correct and 3 incorrect. So it's still going to amount to the same thing. So no matter what circumstance we're working with, we're still going to get that 1/5 to the second power times 4/5 to the third power. Whether it's 1 and 2, 1 and 3, 1 and 4, 1 and 5, 2 and 3, 2, and so on, all those possible pairings of values are each going to have the probability of 1/5 squared times 4/5 cubed. All right, so if I want the probability of getting 2 questions correct, I just got to figure out the number of ways it would take to get 2 questions correct. In this case, 10. So again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I would either add up the 1/5 squared times 4/5 cubed to itself 10 times, or just simply multiply it by 10. Right? So what we're going to get here is 640 out of 3,125. So all of that was just for this one instance. Alright, that's exactly 2 correct. So all that for a drop of blood. That's another movie reference for somebody to gain a bonus point for. Okay, so we don't want to do that by hand ever again. It might be fun, but definitely not on a test. So how can we do this using technology? So in Blackboard, on the left-hand panel, you'll see online calculators. You tap on that, tap on Unit 2 Calculator's Binomial Probability, and you'll see a calculator appears. Right, that asks you for the number of trials, probability of success, minimum number of successes, maximum. And then for exact cases, we just make sure that the minimum and maximum values are the same. And then this binomial dist function will compute the probability for those circumstances. You can see below that we have the mean and all that good stuff. But what I'm going to do is toggle these values so it's consistent with the problem that we're working with. So there are 5 trials. Probability of success is 1 out of 5, which is 0.2. So you can, if it's too much trouble to slide it, it's kind of a cool visual, but to slide it to get to the 0.2, you could just tap into the field here and just type the number in. Right? But one thing you'll notice is if you try to put it in as a fraction, that it takes away the slider ability. Now, you may not care about that, but there will come some instances where you'll want to change the p-value from what it is to something else, in which case you'd have to type it in again. And it's not a big deal, I just figured I'd let you know. All right, I'm just going to leave it as the 0.2 though. It's actually the default setting on this program. Program is a generous term for what this is. Anyway, the number of successes, well, let's check and make sure that we just did what we did correctly. So that was for 2 successes. So if I want this calculator to work the right way, I should make the minimum and maximum values the same. So the A and B values the same. And then that's going to spit out the probability, which is 0.2048. So I just want to take a look and see if that's equivalent. And it is. All right, so now what I want to do is get all the other probabilities without doing any of that work that we just did. All right, so I need for 0, which is a fun looking decimal. You can have decimals and fractions in the same problem if you want, but 0.32768, that would be getting none of them right. Now, a little nifty trick. See how I'm having a hard time getting the A value to land on what I want it to? See how my minimum and maximum values are 0 and 100? If I make this much smaller, I just like to have a little wiggle room, but if I make it much smaller, like 10 or even 5, based on the problem that we're working on, 5 would make sense. it's gonna be easier to get it to land on this, on the value that you want it to, right? Because I made it so that it goes by whole unit steps, right? So you see those, it's hard to see, but you see those little white dots along the track? That's telling Desmos that we're skipping all of the decimal values in between. So, little tip. So 0.4096. Yeah, maybe we don't, just for the look of it. Maybe we don't want to put this here. Maybe we want the 0.2048. I don't know, it's a personal preference thing. 0.0512. 0.0064. And you can see that the probability of you getting a good score on this assessment is getting lower and lower as you increase the number of correct answers. Because to get 5 correct answers just by guessing, you wouldn't expect it to be a large probability. All right. So these values, these probability values, they should actually add up to a 1, because this is a probability distribution. All right. So it's something we could actually verify. If we want, and we do, we can go back to the other probability calculator, the probability distribution one, and pop in these values from 0 to 5. I got a lot of extra stuff in here that I don't need, but just get the stuff that I do need, 0 to 5. So the first entry would be 0.32768, then 0.4096, 0.2048, 0.0512, 0.0064, and 0.00032. Now there might be some rounding involved here, but if there is, that'll kind of play through in the process. But what I could actually do is I can use the total function, and if I'm ever in doubt with Desmos, I just start typing in the word that I think is a function, total. I want it to total out my y1 values. All right, those are all the probabilities, just to make sure that I got everything accounted for. And you can see when I add up my y1s, those are the probabilities. The sum, so these are my p of x's, the sum of p of x is equal to 1. So this is an appropriate probability distribution. More importantly, it's a nice little checking mechanism to make sure I didn't just screw it up. All right, I've accounted for everything, every variable along the way. All right, but again, this probability calculator or probability distribution calculator will give us the mean of the distribution, mu equals 1, and it'll give us the standard deviation. All right, so the mean is the expected value. This is the expected number of correct answers. I'll say correct guesses on the pop quiz. All right, so that's what you should expect. All right, if you go into a 5-question multiple choice assessment with 5 choices each and guess on every single one of them, you shouldn't expect to get any more than one of them right. All right, and that's consistent with the one that has the largest probability, so that kind of feels right. All right, so this sigma value represents the average displacement. It's the spread of the data set, but it's the average displacement from the mean. We know that this is a comparative value, but it gives us a little bit of a sense of the wiggle room, all right? And it leads us to the unusual values, all right? So I wouldn't expect anything outside of this interval, all right, the usual range, I'll just jot this down here. It didn't ask us, but it's worth noting. Usual values, usual range, negative point, so you expect to get negative credit? I mean, you can get point deductions, but to actually get a test with a negative grade on it, I've only done that once. I'll tell that story in class one of these days. All right, so getting a score over, because we're talking about two. Well, that's the answer. We're talking about discrete values. So the decimal points wouldn't really make sense here, but to get a score over 2 is unusual. So the standard deviation is important in its own right, but it's even more important for what we can gain in terms of the knowledge based off of knowing that standard deviation. All right. So then on the top of the next page, probability of getting at most 2 correct. So for that, I'll go back to my binomial probability calculator. At most 3 means 3 or less. All right, so that means that your setting should be minimum equal to 0, maximum equal to 3. So probability at most 3, I'll make this a 0, and I'll make this a 3. Oh, I said 0. So we're talking about 0.993-ish. All right. So that's really saying that, you know, if 3 out of 5, you look at that as 60%. It's saying that your chances of failing this assessment if you don't study, and you know, how could you study? There were no questions, but you know, just think about the real life analog to this. Is almost, it's over 99% chance that you're going to fail this thing. Right? So, or the best you can do is get a 60%. Now 3 or more, right? So that's at least 3. That's saying minimum value is 3, maximum value is whatever the end value is. In this case, 5. That's the most number of questions that you can get right. All right, so the probability of 3 or more so 3, make this a 5, and you get about 0.0579. All right. Now you'll notice that you can actually scroll this even further than 5. You know, you can make it really large. Once you get to the maximum number of questions that you can get correct, Desmos starts disregarding what you're saying after that. If there's a 5-question test, how are you going to get 10 questions right? You know, it knows. The formula knows. All right, it's irrelevant after that. All right. Now, we also have the mean and standard deviations for binomial distributions. Particular formulas that once you recognize a situation as being binomial, you could use these formulas rather than using that funky calculator that we went over to a couple minutes ago to get these numbers. Mu is equal to just simply n times p. All right, but that's only true if you've accounted for these possible conditions. Let me just bring them over. I didn't want to copy, I wanted to take a screenshot. Now I want to copy. It's all about order of operations. There we are. All right, so again, these are true, so you can use this rule. Number of trials was 5. Probability of success, 1 out of 5. Expected value, 1. Sigma is equal to the square root of n, which is 5, times probability of success, 1 out of 5, Probability of failure, 1 minus 1 out of 5 is 4 out of 5. Pretty solid bet that that's going to be the 0.894, but you could see I've already jotted that into the program here. All right, but you know, maybe you don't believe. Not a believer? I should have convinced you. That's not a movie quote. That's just me being me. But you can see you get that decimal value. So we're talking about 0.894. But what I did, again, was I put all this into the binomial probability calculator so you can get those results without having to do the work. All right. So then the other question would be, would you consider 68 correct questions or answers on a 100 question multiple choice test with 4 choices each? So I'm changing it up a little bit. Unusual. The first thing you'd have to do is look at the conditions, fixed number of trials, yep, 100 questions, fixed probabilities, 4 choices, so 1 in 4 chance of getting it right. Independent events, if you use a choice once, you can use it again. So I'll just put simply a nice little check mark here for each of those. And 2 outcomes, yeah, it's either right or wrong. So that's accounted for also. So if we want to do the mu equals NP and sigma equals NP times 1 minus P, we can. You don't even have to really use a fancy Desmos calculator in the sense that you don't have to use, type in all this information if you don't want to. But it's kind of nice if you recognize it. It's a number of trials, max it out. Probability of success, 0.25. I don't need to evaluate any probabilities. I just need to go on down here to get the NP and the square root of NP times 1 minus P. 4.330. All right. Now what I want to do beyond that is figure out what my unusual interval is going to be, or my usual interval. So I need mu plus or minus 2 sigma. It's the same process we've been using all semester. So I would do 25 minus 2 times, we'll just go with the decimal, but I just type it in, old school here. And then 25 plus 2 times 4.33. All right, so our usual interval, or our usual range, about 16.340. I'm going out to 3 decimals, just force a habit. 33.66. Of course, just be mindful of whatever the rounding instructions are on a test. All right, so this is the usual interval. So the usual range. It's saying, would you consider 68 questions correct on a 100 question multiple choice test to be unusual? Yeah. It shouldn't be anywhere near that. All right, so therefore 68 correct is unusual. All right. But all based off of the fact that we've met the conditions of a binomial distribution.